I would like to discuss at this moment how to calculate the time complexities of any programs. Okay, so that is very important. So throughout this entire course, we will be calculating time complexities of lot of problems. This is the first time we are starting how to find out the time complexities. Correct? So please recall all the notations before attending this lecture. Definitely you should have attended order notation, I mean that asymptotic notations, order, omega, theta. At least these three things you should know, order, omega, theta. Okay. Now I will tell you first of all when to use order, when to use omega, when to use theta. Okay. So my assumption is already you know these things. Order for less than or equal to, omega for greater than or equal to, theta for equal to. Example, let's say you calculated running time of the program already. Okay. Now, if that program's running time, whatever, doesn't matter. If that program's running time is, let's say, some n or n square, n cube like this. Okay. Then, example, strictly it is n for any input, like whatever the input you take, always it is giving you n, otherwise 2n are always a class of n. You know what are the values which belongs to class n? What are they? N, 2n, 3n, because we ignore the constants, right? So whenever you get n or 2n or 3n, that kind of thing, then simply say that your running time is equal to class n, correct? Whenever you want to say that your running time is equal to class n, we say theta of n. That's why your running time, let's say f of n, we say theta of n. That is correct. This is a proper usage. Now, whenever you want to say that, whenever you want to use order, then definitely your intention is less than or equal to. Your program's running time is less than or equal to something, then use order of n. Try to understand the difference. Example, your program's running time is n always. Then question number 1, can I say that your program's running time is less than or equal to n? Can I say that? Yes. Then directly go for this notation, f of n equal to order of n. Sir, you said f of n is theta of n? Yes, because your program's running time is always equal to n. Yes or no? That's why go for theta of n. That is also correct. When any program's running time is always equal to some n, then you say f of n equal to theta of n. If it is always less than or equal to n, then go for order of n. That is, it's all depends on your perception. What do you want to say, right? So third one, omega of n. Example, you want to say that your program's running time, you know that it is greater than or equal to n, let's say, always. Then you can say f of n equal to omega of n usually. So this is a way you can use the notations. Understand? Now, let's take one example. Example, let's say I have a program, its running time, sometimes n square, sometimes n cube. These are the only possibilities. Okay. Then in this scenario, first, can I say f of n equal to theta of n is the question. We'll see. If f of n equal to theta of n, that means what? When to use it? Already I told you. Whenever your program's running time is equal to n, always, then use theta. But your program's running time is not always n, right? Sometimes n square, sometimes n cube. That's why this is absolutely wrong. Sir, can I say f of n equal to order of n in this situation? We'll see. To say f of n equal to order of n, your program's running time should be always less than or equal to n. No, sometimes it is n square, n cube. N square and n cube are, greater than n, right? That's why this is also wrong. Then only possibility, you can say f of n equal to omega of n, I guess. Check it out. So to say f of n equal to omega of n, then f of n definitely should be greater than or equal to n. Check it out. Your program's running time is greater than or equal to n, correct or not? Yes. Then it is perfect. Finally, in that way easily we can find out the right notation for the right running time. Now we'll see one more example. Let's say one program's running time is n square sometimes, 2n square sometimes, 3n square sometimes, 4n square time sometimes. Now the question number 1, can I say my program's running time f of n is, let's say f of n is program's running time, is it theta of n square? Absolutely. Because yes, n square is theta of n square equal to n square, 2n square also theta of n square, 3n square also theta of n square, 4n square also theta of n square. That's why, so constant doesn't matter. So it's like always n square, n square, n square. Whenever your program's running time is always n square, then you simply say it is theta of n square. Now in this situation, can I say f of n equal to order of n square? What is f of n here? So your f of n is like sometimes n square, again sometimes n square, every time n square, right? So if I summarize it, your program's running time is n square. Is that n square is less than or equal to n square? Absolutely, again correct. That's why we can use order. Not a problem. Similarly, you can also say f of n equal to omega of n square here. Why? Check it out. Your program's running time is n square always. Such n square, is it always omega means greater than or equal to? Always greater than or equal to n square? Yes. Then we can say omega also, right? So finally, whenever your program's running time is n square, like this, n square or 2n square, anything like n square class, then we say that f of n is theta of n square, order of n square, omega of n square. Now, one more example. Let's say your program's running time is n square sometimes, n cube sometimes, n to the power of 4 and n to the power of 5. Now we'll see. Question number 1. Can I say f of n equal to theta of n to the power of 5? Absolutely wrong. The reason, your program's running time is varying from n square to n power 5. Is it always n power 5? No. Then don't go for theta, because theta is for, equality. Is it always equal to n power 5? No. Absolutely false. No. Can I say theta of n to the power of 4? No. You can't say any of the theta. Like you can't say theta of n power 5. You can't say theta of n power 4, because it is varying from n square to n power 5. Then you can only go for, in this situation only you can go for order notation and omega notation. So let's try order. So my program's running time f of n is order of n cube. It's like you are saying that your program's running time is always less than or equal to n cube, because order denotes less than or equal to. Is your program always less than or equal to n cube? No, sometimes more than that. Correct? See, n power 4, n power 5. Then how can you say that your program's running time is less than or equal to n cube? That's why it is false. Now, can I say f of n equal to order of n square? We'll see. That means less than or equal to n square. Yeah, my program's running time is always less than or equal to n square. Yes, absolutely. Is it always less than or equal to n square? No. Sometimes it is greater than n square. This is also wrong. Correct? So final touch. So what to do then? Really I want to do use order notation. Then what to do? You simply say f of n equal to order of n power 5. Check it out. So it is definitely correct. Why? F of n less than or equal to n power 5. Your program's running time, is it not less than or equal to n power 5? Is it more than n power 5? No. Is it not always less than or equal to n power 5? Yes, that's why it is correct. So finally, whenever you have variable running times, simply take the highest value and write order. Then only it works. So we say f of n equal to order of n power 5. Simple. Less than or equal to n power 5. That's why order of n power 5. Now, is it not always greater than or equal to n square? Yes, that's why simply say f of n greater than or equal to n square. Always. That's why greater than or equal to means omega. But theta will not work. Understand? So finally, we can use theta only if you have, running time, constant running time, like, always same running time. Then we can go for theta. If you have a variable running time like this, then either you have to go for order notation or omega. So order of highest value, omega of lowest value will work generally. So this is the way you can interpret order omega theta. Okay. Now I'm going to use this order omega theta throughout the this course. Now we'll see how to analyze the running time of a program. So far we have not written very big programs, right? We started, right? From stack onwards we write so many algorithms and we have to find out the time complexities of them. So usually students get a lot of confusion. So how to analyze the time complexities? It is very easy. Be confident and simply focus. Okay. So first thing, whenever you write a program, there are some arithmetic operations like addition, subtraction, multiplication. All that operation generally takes 1 unit of computer time. Okay. So that's why I want to separate this analysis from computer details like machine details. Like is your computer super computer like Pentium processor, otherwise very slow processor, it should not affect our time complexities. That's why generally what we do is we assume that whatever the computer you take, usually this addition, subtractions, divisions, everything takes some constant time. Okay. Now one more thing. If you do comparisons or assignments, example, if you write A equal to B in C programming, then it takes 1 unit of time. If the data is integer or character for primitive data types. If you have array, but don't say that, sir, if I copy one array from one array to another array, then that might take lot of time. The reason here, assignment from one primitive data type to another primitive data type is 1 unit. That means integer to integer data transfer or character to character, otherwise floating point to floating point. All these are all called primitive assignments. They take only 1 unit of time. But don't do this thing. So take a structure 1, structure 2, and you can copy. If you write S1 equal to S2, where S1 and S2 are structures, then if you copy, then that might take lot of time. Don't say it is constant. Okay, so that's why only observe the primitive operations. So primitive operations, I mean assignment of primitive operations is constant. Okay, now so one more thing, in program whenever you see return statement, okay, return some value, but you are not computing the value, already value is computed. To just when you have a already computed value and to return, to execute this line, it takes only 1 unit of time, some constant time. Okay, just remember it. Okay, but sometimes people again get confusion. Sir, in this return, I have a function call. Yes, but to compute that function call, it might take lot of time. So what you do is first compute that function call and first calculate the time complexity of that. Okay, then you add that to the time complexity of your overall thing. That's why. So let's leave it, like forget about this function call. If there is a function call, then how to analyze the time complexity of that function call is a separate issue, right? That we will be learning again, right? That also we do. But if you have already, let's say you calculated the time complexity of that function, once function is evaluated, then you get a value, right? So to return that value, it takes only constant time. But to evaluate that function, how much time it will take? Again, we have to do with these things. Okay, take that function and start the rules again. If that function contains addition, subtraction, anything, anywhere, then they take only constant time. Assignments, constant time, but assignments should be between primitive data operations, right? Now, apart from that, comparisons. Example, to compare any these are all about primitive data types like integer, character, and float. I'm talking about, and double, right? These are all called primitive data units. Between them, if there is a comparison like x equal to y, okay, x equal to y, so that takes only 1 unit of time. Understand? So assignments, comparisons, and multiplication between again primitive data types definitely takes only constant time. If you know that thing, then easily we can find out the time complexity of anything. Now, so let's begin with this idea, and whenever you see some complicated things, okay, then I will explain, remaining things. If we encounter something new, then we'll see that later. But let's start with this idea. Whatever you learn with that, if you go, definitely we can solve the time complexities. What we do is throughout this course, we will be taking lot of algorithms and we are analyzing. While doing that, automatically you learn how to find out the time complexity of a program. Okay, let's begin. Example. This, what is the time complexity of E stack empty? Okay, now start. First of all, what happens? First understand the program. If you understand the program, you realize that we are passing some address to this PS first. After all, it takes 1 unit of time because we are just passing address from one place to another place. Again, it's a primitive operation, right? It's a 32-bit data, right? So that's why it takes only 1 unit. We are not copying the data, this entire structure to here. Please remember, that takes lot of time. Here we are after all taking this entire data's address. It takes 1 unit of time. Let me calculate 1 unit plus come here. Control comes here and there is a if condition. What is the time complexity of if condition? So do line by line, that's it. When you have a program, calculate the time complexity of every line. What is the time complexity of this line if it is executed? In if, what are you doing? After all, you are doing comparison. Already I told you PS cap top is a primitive data, minus 1 is a constant. Comparison between these two definitely takes only 1 unit of time. That is our assumption already. Now returning 1, returning a constant value takes only 1 unit of time. Else returning 0 also takes 1 unit of time. In the worst case, that means in the worst case means where you generally take lot of time. What is the maximum time you might take in this program? Control comes here, then you don't come here, then you go to else part and you go here, right? That is the longest thing. Even in that also, after all you are spending, if you do everything also, like this one, this one, this one, this one, this one, after all 5 units. Of course we don't do that, but if I do also, then it's after all 5 units. 5 is a constant. That's why I can say that this method's time complexity, if it is called, takes only 5 units, also known as constant. Generally, if your time complexity of any program is 1 or 2 or 3, any constant, even 1 crore also, we represent it with 1. Okay, I will tell you what is the reason. We say order of 1. Why it is order of 1 is a question. Simple. Already we proved that any constant, you take 1 crore. So 1 crore is order of 1. If you have a doubt, please attend my asymptotic notation lectures. Already I proved there. So any constant is order of 1. Okay. So if you don't want to attend that lectures, then remember it. Okay. Next, from now onwards, whenever I see constant, I write order of 1. Second thing, this is theta of 1 also. 1 crore is theta of 1. That 1 crore is omega of 1 also. To understand that, please go through order omega theta notations. Right. So at this moment, from now onwards, whenever I see constant, I write order of 1, otherwise omega of 1, otherwise theta of 1. All are true. Understand? Now this program or methods time complexity order of 1. Now in the same way, we'll see this one. After all, here one pointer copy, 1 unit, then 1 unit for comparison. Returning takes 1 unit. This return takes 1 unit. Either you execute this return or this return, correct? That's why at most 1, 2, 3. 3 operations, correct? So that's why I can say that 3 or 4 or 5 all are constant. Then constant can be written as order of 1. That's why this method's time complexity order of 1. Understand? Now